Okay, we want to look at a rational function, a polynomial divided by a polynomial. The rational function will have zeros when the numerator polynomial is 0 and the denominator function isn't 0. Now, of course, we can factor the numerator, factor the denominator. We can divide out identical factors, factors of the numerator which are identical to factors of the denominator. And our simplified function would then satisfy the fact that, well, we have zeros only where the simplified function has zeros, which will occur only when the numerator of the simplified function is 0. If we do divide out a factor of the numerator by a factor of the denominator, the function is still undefined at the point at the zero, at any zero of the denominator of the original function, because of course you can't have division by 0. So you want to kind of keep that in mind, but other than that, the zeros will occur only when the numerator polynomial is 0, the denominator isn't. Those can occur at zeros of the simplified function, but if there's a 0 of the simplified function at which the original function was undefined, then you have an undefined point for that function, and not a 0. Okay, you're going to get vertical asymptotes anytime when the denominator of the simplified function is 0. You won't get a vertical asymptote when the denominator of the original function is 0 if it's matched by 0 of the numerator. Okay, you have holes where the denominator of the original function is 0. Whether the denominator of the simplified function would be 0 at that point or not. Okay, well, a picture then of the zeros and the vertical asymptotes of the original function would look something like this. Okay, we've got a 0 here, a 0 here, a 0 here, and a 0 here. We got vertical asymptotes here, here, and here. And the vertical asymptotes, again, are the points at which the derivative, the denominator is 0, the numerator isn't. Now, I should also indicate holes of the function, because not every 0 of the denominator constitutes a 0, or constitutes a vertical asymptote. However, at a hole, you're not going to get a sign change. At a hole that isn't a vertical asymptote, you won't get a sign change, because you're just going to have factors of the denominator dividing factors of the numerator, and the factor of the denominator that divides the factor of the numerator is going to have the same sign. And you're not going to get a sign change. I don't want to go into too much detail on that. Let's just say it's safe to say that the sign of a rational function can change only at a 0 or at a vertical asymptote. And this goes back to the fact that both of these polynomials factor into linear and irreducible quadratic factors. Okay. Now, if the degree of the denominator is greater than the degree of the numerator, then also the positive x-axis is going to be a horizontal asymptote. If not, then you're going to have to worry about what happens to the side of the function as you go to the right of the greatest 0 or asymptote, or to the left of the least 0 or asymptote, and determine whether the function goes to infinity or negative infinity at that point, much in the same way you would for a polynomial. Okay, so in this case, excuse me, I just hesitated there because I think there's something wrong with this graph, and we'll talk about that when we get to that point. I can modify it easily. Okay, we have a case where we have zeros at these 3 points. We have vertical asymptotes at these 3 points. Now, one possibility is that we have an asymptote that approaches this vertical line through negative y values on the left side and through positive y values on the right side. Okay, then comes down here, goes through a 0 here, turns around, maybe goes through the 0, but in this case we're going to assume that the polynomial or the rational function hits a 0 here, but much in a parabolic fashion, corresponding to a couple of linear factors at that point. Then goes through the y-intercept, and I kind of missed the y-intercept. I should have gone right through it. Down through negative values here, where it's asymptotic to this vertical line, comes up from negative values at this line, goes through 0, back up through positive values, and then flips over on the other side of the vertical asymptote here, comes up through 0, and then goes off toward positive infinity. Now, there is a problem with the way I drew that, because it appears that maybe we're approaching a horizontal asymptote with the negative x-axis here, and we can't do that. And correct me if I'm not thinking correctly, but I don't think we can do that because the only way that would happen is if the degree of the denominator was greater than the degree of the numerator. If that's the case, then we're not going to go off toward infinity here. And you can think about why that's true, but I'm going to just extend this graph a little more to indicate that it's now heading toward negative infinity here, or to at least imply that, and that the graph does not come up above the x-axis here, because in that case we'd have another 0 over here. Okay, so just suffice it to say that if this thing tends off then toward negative infinity on this side, then it can tend off toward positive infinity on this side, and I don't have a contradiction. The only places the graph can change sign are at asymptotes, as happens here, at zeros, which happens here, and here, and here. Now we have an asymptote here where we don't change sign. It's negative on this side, negative on this side. You can think about how that would happen, but would it be a couple of matching linear factors in the denominator? We have a 0 here at which we don't change sign, and we've seen that with polynomials. But let's just leave it at this, that this is a typical way you would begin analyzing a rational function, and we've gone through all the details of understanding these zeros and asymptotes in the many examples we've done in class, and you can always review the corresponding videos. Again then, we have intervals where the graph has constant sign. Those are the intervals between and to the left of the leftmost and to the right of the rightmost vertical asymptote and or 0. We see that behavior exhibited here. To the left of the leftmost asymptote or 0, the graph is negative. Between this asymptote and this 0, the graph is always positive. Between this asymptote, between this 0 and this 0, it's negative. Between this 0 and this asymptote, it's negative. Between this asymptote and this 0, it's negative. Goes positive here. Between this 0 and this asymptote is negative. Between this asymptote and this 0, and then positive to the right of that 0. Constant sign on every interval between consecutive asymptotes and or zeros.